In this lecture, we'll discuss thiols and sulfides. So why thiols? So thiols and sulfides come from the common compound sulfur. Why is sulfur important? If you look at the periodic table, you look at oxygen, and right below in the same group you find sulfur. So you notice that there is some similarity in character. So there is a similarity in character of the way the compounds behave. So to make sure that we can understand this, let's discuss what a thiol is and what a sulfide is. So a thiol in general, so a sulfur in general appears under the oxygen on the periodic table. So thiols in general is basically a sulfur analog of alcohol. So for example, if you take a dash OH, we call this an alcohol. But when you say the same dash SH in place of oxygen, we call this a thiol. So we call this a thiol. So for example, when we name this, we call it 3-methyl-1-butanol. But here when we have SH, what we do here is we do the same thing, 3-methyl-1-butane thiol. So notice that it still gets the first priority. So you still get the same numbering pattern. But the difference here is that we take in place of ol, we put it as thiol. So word thiol refers to the SH sulfur and hydrogen. So and behaves the same way, and these thiols in general are called mercaptans. So we'll come back to this why it's called mercaptans. The reason is because they have the ability to capture mercury. So that's the reason why some of the compounds that you might see as thiols are generally used for mercury poisoning. So for example, the prefix that is used for SH is mercapto. So for example, if you want to use SH as a side group, as a substituent group, so for example, you have an alcohol group, so we always have to give priority to the alcohol group. So 1, 2, 3 and 4. So in place of SH now, what do we write here? We write 3-mercapto and then write 3-methyl-1-butanol. Next, the other compound is dimercaprol, so where you have two SH groups. So this is 2,3-dimercapto-1-propanol. So this is a compound that's commonly used to treat mercury poisoning. So that is where the name also refers from. So that is where the name also comes from. So thiols in general are known to have a very unpleasant odor. So an example of that would be skunks. So skunks use thiols as a spraying mechanism and a defense mechanism for the prey that come near them. So because of the unpleasant odor and because of the property that they last for a really long time, they are generally used as a natural self-defense mechanism. And methane thiol is generally added to the natural gas so that whenever it leaks, you can detect. So this is also a common compound that's used in your liquid petroleum gas as well, the LPG cylinders that you use at home. So the general gas that you use does not have any smell. So to make sure that when it leaks that there is a smell, we generally put in an extra substituent compound. That substituent compound is responsible for the odor or the bad odor that you get when you have a gas leak. So the hydrosulfide ion is a strong nucleophile and a weak base. So focus on this, it's a strong nucleophile and it's a weak base. Why is it a strong nucleophile? Notice that sulfur has the same number of electrons as that of oxygen, but sulfur is larger. So sulfur is larger in size. Because it's larger in size, it's easy to be a better nucleophile because it's ready to donate its pair of electrons. So it's ready to donate its pair of electrons. This is one of the reasons why SH is a good nucleophile and a strong nucleophile, but a weak base. The reason it's a weak base is it does not have enough energy to accept a proton. So it tries to, it's always so the idea here is to look at H2S. H2S is a strong acid. So it's a stronger acid. And SH minus becomes a weak base. So remember that this SH minus is the conjugate base of H2S. So it's a conjugate base. Because it's a conjugate base, the stronger acid becomes a weaker base. Now, so primary and secondary thiols you can synthesize from common SN2 reactions by using sodium hydrosulfide. So with an alkyl halide. So for example, you have alkyl halide, and if you mix it with NaSH, the SH minus ion acting as a nucleophile will come and attack the bromine, and bromine will go out. So this here is the idea behind the SN2 reaction. Now if the compound, the carbon is a chiral center, then it will automatically alter the configuration where it changes from R to S or S to R. So it will always try to change the chirality of the compound. So thiols and sulfides in general thiols are generally oxidized to form what we call disulfides in presence of bromine under basic conditions. If you take two compounds of thiols and mix it in presence of NaOH H2O and bromine, it creates a disulfide. So there are two main reactions that occur, and both of them are SN2 reactions. So both of them here are going to be SN2 reactions. So let's take a simple example. So if you take a general, for example, let's say so if you take SH plus SH. So the idea here is that the final compound in presence of NaOH and H2O and in the presence of bromine creates a disulfide where sulfur bonds to the sulfur and creates the final compound. So what happens here is that the first thing that happens is that if you take this SH undergoes a SN2 reaction in presence of bromine. So what happens here is that this carbon, so the carbon here, the sulfur here, tries to take the electrons from sulfur. So the hydrogen, notice that SH is somewhat like this. So what happens here is that SH, sulfur being a larger compound, will try to attract the electrons towards itself, and the hydrogen goes out. So this results in the formation of sulfur with 6 electrons. So this sulfur with 6 electrons now attacks the bromine ion, so the bromine, and the bromine in general donates its electrons back to the other bromine and causes it to create a intermediate compound where it creates Br. But here the problem is this is generally going to be unstable because bromine is highly electronegative in comparison to sulfur. So what will happen now is another compound of this S minus will come and attack bromine. Will come and attack so the sulfur here will come and attack the sulfur again. When it attacks the sulfur, this compound again leaves its electrons and bromine goes out. So when finally the reaction ends, you end up with sulfur bonded to another sulfur and has 2 pairs of electrons each. This is the final compound that you end up with. The reason why this H goes away is because of the presence of NaOH. So the OH minus will attack the proton and it will undergo proton transfer. So here this is the final compound. So this here is a compound of disulfide. So this is the compound of disulfide. So these disulfides you can reduce them to corresponding diodes by using HCl and zinc. So the interconversion between thiol and disulfide can also occur directly via the free radical mechanism, where the hydrogens lose the electrons each and the sulfurs lose their electrons, and the bond dissociation occurs. And once the bond dissociates, it's only a really small amount, so it can easily be made and also be broken. So the shape of proteins in general relies on this specific bond to be easily broken. So in some amino acids you will contain a sulfur thiol a thiol and a sulfide bond. That sulfide bond is responsible for breaking the protein. Next, so sulfur analogues of ethers are generally called sulfides. For example, if you take a general ether, you end up with RO R dash. So this here is the example of an ether. All sulfur, in place of oxygen, just replace the sulfur. So sulfur becomes the ether becomes a sulfide. So the exact same compound, but here when you name it as a side chain substituent, so we call it an alkoxy group or a methoxy. For example, here it's OCH3, we write methoxy, but when it is SCH3, we will write methyl thio group. So when you write the substituent name, we'll write it methoxy when you have OCH3. When you have SCH3, you write methyl thio. Next, sulfides are generally prepared by nucleophilic attack of the thiolate of an alkyl halide. So you can create a disulfide by attacking with a thiolate of an alkyl halide. So for example, the Rs minus will attack the R. So the R then donates its electrons back to the X. That results in the formation of the sulfide. So this here is an example of the thiolate ion attacking the. So this is the thiolate ion. So thiolate ions are created from thiols under proton transfer. So when they undergo proton transfer, they create the thiolate ion. So under deprotonation, let me write it clearly. Under deprotonation forms the thiolate ion. And the deprotonation is generally done by using NaOH, because NaOH has OH that can capture the proton. So sulfides also undergo a number of reactions. So the first thing that they undergo is they can undergo a substitution reaction with an SN2 mechanism with an alkyl halide. So where they end up bonding and form the sulfide ion or the sulfonium ion. So they end up forming the sulfonium ion. Next, this sulfonium ions, the product in general is a strong alkylating reagent. So what it does is basically it can add an alkyl group to a variety of nucleophiles. For example, when you have a nucleophile nearby, this sulfonium ion will attack the nucleophile. The nucleophile will basically take the CH3 away from the sulfide. So creating the sulfide back again and the nucleophiles, so nucleophilic alkyl group. So sulfides in general can also be oxidized to form sulfoxides and sulfones. So sulfide in general, when you add oxygen, it forms sulfoxide. So sulfoxide is where the sulfur contains two oxygen, double bond of oxygen. A sulfone is where it contains two double bonds of oxygen. So the choice of this oxidizing reagent depends on whether one needs to make a sulfoxide or a sulfone, because the extent of oxidation determines the agent. So determines the agent that we use. So for example, if you want to form a sulfoxide, we use a specific agent. When you want to form a sulfone, we use a specific agent. So for example, sodium metaperidate can be used to form sulfoxide. So metaperidate is NaIO4. So this is the common agent that you can use to form sulfoxide. But whenever you want to form sulfone, we have to use hydrogen peroxide. Why is that the case? Is because the mechanism allows addition of oxygens much higher in hydrogen peroxide, using a hydrogen peroxide, than that of sodium metaperidate. So this compound adds up two oxygens on the sulfur. So this is the common mechanism here. But the problem here, notice that this S double bond O in general is a very little double bond character. The reason mainly is because both of them have the same character, meaning that both of them have a property of forming double bonds, but they are not readily easily able to form double bonds, because you have 2p orbital that's forming an oxygen overlap with a larger 3p orbital. So which means they cannot have much of a reliability. So what happens here is that it always creates a resonant form where the oxygen takes up the electrons and forms the negative charge, and sulfur loses the electrons to form a positive charge. So, and also the same thing with sulfones, where the sulfur gets a higher positive charge with oxygens getting the negative charge. So this here is the characteristic of those compounds. Next, because sulfides are generally readily oxidized, they also make good reducing agents. So one of them is DMS. dimethyl sulfoxide. So is a common compound that's used to reduce ozonide to complete an ozonolysis reaction. For example, if you take an alkene and add ozone to that and finally mix it with dimethyl sulfoxide, you end up forming a ketone, an aldehyde, and DMSO. DMSO is a common aprotic solvent. So that's generally used for SN2 reactions. So there is a common aprotic solvent that's used for SN2 reactions. So this is the idea behind the ozonolysis. So ozonolysis reaction. So it basically splits the double bond into two parts and creates one half of it to be a ketone and the other half becomes an aldehyde. And finally the rest of the oxygen, the other oxygen will end up combining with dimethyl sulfoxide. So dimethyl sulfide and forms dimethyl sulfoxide. So here remember that this is dimethyl sulfide and here it is dimethyl sulfoxide. So this here is the idea behind the compounds. So let's talk about the synthesis strategies using epoxides. Epoxides are one of the most versatile compounds. The reason is because it allows us to install two different functional groups on adjacent carbons. So when you look at the actual epoxide and when you split open the cycle, in the ring opening of the cycle, if you take a nucleophile, the nucleophile will attach itself to any one of the adjacent carbons, whichever is the less hindered carbon, and the other side gets a OH group. So whenever you see two adjacent functional groups, you should think of an epoxide. This is the idea here, especially made from an alkane. So for example, when you see an alkene, you can think that from the alkene we start going to formation of an epoxide. So here we use mercapto, peroxybutyl benzoic acid, and you use sodium cyanide. So this here causes it to create an epoxide. And in the second step, the cyanide becomes the nucleophile and then attaches itself onto the epoxide atom. So this here is the idea behind the synthesis strategy. So by reacting an epoxide with a Grignard reagent, so you can modify the carbon skeleton. So when you have a bromide, so for example the starting material, the first thing that you do is put it in magnesium diethyl ether, which creates a Grignard reagent, and then react it with epoxide. So when you react it with epoxide, then the R attaches itself onto the carbon skeleton, meaning that you are extending the original skeleton to other extra atoms. So think of an alkyl halide as the starting material to which carbons will be added via the Grignard reagent. So the epoxide consists of carbon chain that will be added to the alkyl halide. So this here is the idea behind the use of epoxides with Grignard reagents. So the first step we talked about, when you have two adjacent functional groups, then we can use it to, the epoxides are useful. So you can make use of epoxides, especially when you're starting with an alkene. Next, an epoxide yields a longer carbon chain, so with a functional group of the second carbon of the newly installed chain. So here, if you have a carbonyl, that would be useful as a functional group of the first carbon, so a newly installed part of the chain. So for example, when you have RBr, you start a Grignard reagent, and then if you add a general carbonyl group, the carbonyl group itself forms an OH group, and then the R adds itself onto the chain. So in place of the hydrogen, you end up with a R chain. The R chain is the skeletal carbon chain, and the hydrogen, the water molecule, is used to reduce the oxygen into OH. So consider the reagents necessary here. So we are starting with benzoyl bromide, so the phenyl bromide, and we want to form a compound that's much more complex. So to achieve this reaction, what are the steps that you will need? So pause the video right here and try to see what are the steps that you will likely use to accomplish this process. Now let's look at the reaction. So we start with, again, magnesium bromide, magnesium and ether, which creates the Grignard reagent. And in the second step, we will have to use a epoxide. Now the epoxide here that we use has to have some sort of resemblance. Notice that the bromine has to be separated. So which means that this, in the place of that carbon, you will have to attach a longer structure, which means you need 3 carbon structure. Now, originally a general epoxide would only contain 2 carbons, so we'll add a third carbon here. And once you add that, you have an oxygen group. That oxygen group becomes the OH group, so which the H3O plus work up. So this is how you end up forming the final compound. So these are the common ones that are used. So again, I'll repeat it again. So you can use an epoxide when you want to put 2 functional groups, or you can use an epoxide and a Grignard reagent to create a longer carbon chain. So this is the idea behind the synthesis strategies with epoxides.